Hi, I'm Ms. Vu, and today we're going to look at when is a function differentiable. Is a function differentiable? When is a function differentiable? We had a look at this example last year, but let's revisit this. Which of these graphs is differentiable at x equals 0? I'm going to give you some time to have a look at this. So here we have three hybrid functions. Over here we have -1 before x reaches 0, and after x reaches 0 we have 1. Here we have a linear, 2x plus 1 before x reaches 0, and after x reaches 0 we have a quadratic. It curves a bit, but it's hard to see because we only have a little bit. And here we have another two linears, and one is 2x plus 2 before x equals 0, and minus 2x plus 2 after x equals 0. So which of these are differentiable when x equals to 0 at that point there? Is it differentiable at this point, and this point? So for the first one, we can see that the graph of the derivative, the gradient here is 0, the gradient here is 0, is always 0 except for at the point x equals 0. There's no gradient there. For this graph, the gradient here is a positive constant, whereas over here it's positive, but it's getting steeper, so more positive, more positive. So the graph is going to look like a positive value, and then it's going to be positive, but more and more positive. So the y value increases. So constant there, and then upwards because the y value increases. And the last one, we have a positive value there, and we have a negative value there. So constant values, so a positive gradient before x equals 0 and a negative gradient at x equals 0. So when we look at the gradient graphs, we can clearly see that there's no gradient here at this point here, but there is a gradient at this point. And over here, the gradients don't exist because it doesn't match. There's no value there. So last year we had a look at this statement here. The gradient exists if for the function the limit at h approaches 0 for f of x plus h minus f of x over h exists. No gradient because x equals 0 for the derivative, and here at x equals 0 the left gradient is not the same as the right gradient. They're not approaching the same value. So what was the two things that we said for it to be differentiable? Well, firstly, a function is said to be differentiable at a point A with the statement before, but the other two things we said were it is continuous and it is smooth. Let's define the word smooth, because in the previous example, smooth just looked like that. But how do you tell if it's actually not smooth? How would you describe that? So not smooth is when it fails this, or smooth is when this is true. So let's have a look at this. This is a hybrid function. There's a function before at a point A and another function after point A. So at point A, so the point where the two lines meet, the derivative of the left side should be equal to the derivative of the right side. If that's true, then it's smooth. So let's have a look at the graph before. See, the number from the left is the same as the number on the right. The derivatives on the left is the same as the derivative on the right. Then we say this one is smooth. So this one is not continuous. The graph, not the gradient, I'm talking about the graph, is not continuous. So we don't even care whether it's smooth or not. It will not have a gradient. Whereas this one is continuous, then we check if it's smooth. And we see that it is smooth. The gradients from both sides is the same. Whereas this one, it is continuous, but we clearly see that it's not smooth because the gradient from both sides are not the same. So we say that this graph here, not the derivative, the graph here is differentiable for all values except for 0. This one is differentiable for all values, and this one is differentiable for all values except for 0. Or you can write, instead of the word differentiable, f dash x exists or defined for the domain that we mentioned. Again, this is an example from last year. Let's do a little bit of recall warm-up. So determine if the function is continuous, differentiable, both or neither at the certain point. So obviously the point where it's slightly different. You can pause the video and give it a go yourself and then unpause to check your answers. So here we have at x equals 3, it's not continuous, it breaks. So therefore it's not differentiable. The easiest way to see if it's continuous is put your finger on the graph, and if you have to lift it, then it's not continuous. So at x equals 1, you have to lift your hand because there's a hole there, it's not continuous. At x equals 0, it's a black dot, so we do go past that point. So it is continuous and it is a smooth section, so it is differentiable as well. At x equals 0, we can see that it is continuous, but it's not smooth, so it is not differentiable. Over here, we lift up pen or finger to go to the next part, so it's not continuous and therefore not differentiable. This one, it is continuous, but again it's sharp, so it is not differentiable. This one is the same as that. And here's a tricky one. It is continuous at -1, definitely, and it looks smooth, but what is the gradient here? What is it 0? What's that? Oops. What's that gradient? That is undefined, so it's not differentiable. Be careful with that one. Let's do an example. State the set of values for which the derivative is defined. Sketch both the original function and its derivative on the same set of axes. So before x equals 0, we have a linear, and after x equals 0, we have a quadratic. Let's have a look at the derivative. Notice that we need to define the domain for each part as well. For here, the derivative is just 2, whereas here, derive that, you get 2x plus 2 for x is greater than 0. Now, for the derivative at 0, we have to check. For up here is 2. For down here, when x is 0, we have 2. So it is continuous. So the domain doesn't really change, and it doesn't matter because it's differentiable at that point. So let's sketch it. So for f of x, 2x plus 1, it looks like that. Positive gradient intersect at 1. Then the quadratic, when x equals 0 for here, we have an intercept of 1. So it starts here and it curves. For the derivative, we have 2x plus 2. So before 0, it's a value of 2 over here. And afterwards, it is 2x plus 2. So positive gradient going through 2. Now notice that you label as the derivative and f of x, so you know which line represents what. So x is differentiable for all values, all real values. Example 3. So a similar example, but this time we have minus x and x. So the derivative on top is -1, the derivative on the bottom is 1. Are the derivatives the same at x equals 0? No, they're not. So because they're not the same, the domain is not inclusive of 0. The derivative is not available at x equals 0. So you cannot put equals there. It doesn't exist. So the derivative of 0, we have two different values. So -1 and 1. So it's not smooth. So it doesn't exist. So let's sketch this. So before 0, we have negative x. After 0, we have positive x. The gradient here is -1. The gradient here is +1. So the gradient has a white circle or a hole at x equals 0. So the graph is differentiable at all values except for 0. So let's have a look at example 4. This time we're doing a cubic and a quadratic. The gradient for x cubed is 3x squared, and the gradient for the bottom part, x squared, is 2x. Let's find out at the joining point whether they have a common gradient. So let's look at the gradient at 0. We have 0 and 0. So the gradient does exist at 0. And we can sketch this to double check it. So here, the original equation, x cubed and x squared plus 0, it looks smooth. So let's see if it exists, the gradient. So it's a positive value, then the gradient becomes closer and closer, still positive, but closer to 0. So it's going to be a big number and then closer to 0. Over here, it is increasing at a constant rate. So here we have from 0 to bigger and bigger. So you can see that the gradient does have a value there of the same from the left side and the right side. We do have a gradient at 0. And in the original graph, the blue line, we can see that it is smooth there. Example 5, for the following function, x to the power third, determine the derivative. So bring the third to the front and do power of a third minus 1. So a third minus 1 is minus 2/3. And we like positive power, so we're going to bring that to the bottom. So the third, x to the 2/3. State the values for which x has a derivative. Now, this is the derivative. This is the original function. Have a look at the derivative. For what value of x will this work? All values except for when x is 0. If we have x is 0, then we'll have 1/0, which doesn't work. So the derivative, x can be anything but 0. So the derivative is for all values except for 0, and the equation is 1/3, x to the power 2/3. Now let's go to the CAS, and let's sketch this. Let's go to graphs. So our original equation was x to the power of a third, and it looks something like that. And our derivative is 1/3x to the power of 2/3. Let's sketch the derivative. Before we do that, we can see that the gradient is going to be close to 0, getting more positive, undefined, and then big number, then getting smaller again. So again, 0 getting bigger, undefined, and then bigger and getting smaller. Let's see if it looks like what we expected. There it is. So we have big value getting smaller and then bigger again. So remember that 0 doesn't exist, but it's very hard to see on the CAS. So make sure that you can calculate that yourself. I wonder if we can zoom in. So the shape is a little bit more prominent there. You can see that at that point it's undefined. So don't copy that. Make sure you do a little white circle at 0. And turn the CAS off. Okay, that's it for me today. I'm going to leave you guys with 2 more examples from last year, just to practice visualizing gradients graphs from the original graphs. Aside from that, revisit these questions, and I'll see you next time. Bye. Here we have last year's graph. We can see that we can sketch the gradient by first looking at the points where the gradient is 0, which is here and here. So we can do a red dot for 0, where the gradient is 0. And we can see that in between that it's negative, so it's going to be negative underneath the x-axis. And on each side we can see that it's positive, so it's going to be above the x-axis. This is a cubic and the gradient is a quadratic. This is another example from last year. We can see that it's negative gradient, positive, positive. So the first section is negative, positive, negative, positive. And the thing to watch out for is the endpoints of the derivative are white circles, because the derivative does not exist at endpoints. Okay, thank you for watching. See you next time. Bye.